My name is Kumar Rishabh, and this is a presentation on Intel 8085 microprocessor program execution process. Basically, we are going to look at how an Intel 8085 microprocessor makes sense of the instructions or the code given to it and gets the work done. But before diving into its details, we are going to have a quick look at the 8085 basic hardware and the programming model. This figure shows a hardware model and a programming model specific to the 8085 microprocessor. As of now, we are going to mainly focus on the programming model. The programming model consists of some segments of the ALU and the register. This model does not reflect the physical structure of the 8085, but includes the information that is critical in writing the assembly language programs. The model includes 6 registers, 1 accumulator, 1 flag register, as shown in figure. In addition, it has two 16-bit registers, the stack pointer and the program counter. The 6 general-purpose registers store the 8-bit data. The accumulator is a part of the ALU. The flag register contains the 5 flip-flops which are set or reset according to the data condition. These have critical importance in decision-making process of the microprocessor. The program counter and the stack pointer, both of them are 16-bit register used for storing the 16-bit addresses. The 8085 uses 16-bit address bus to send out memory address, a 8-bit data bus to transfer data, and a control bus for timing signals. Now that we are done with this, we can finally move on to some instruction given to the 8085. The 8085 works on an assembly language program. An instruction is basically a binary pattern designed inside a microprocessor to perform a specific function. Group of instructions are called an instruction set, which determines what a microprocessor can do. The 8085 instruction set can be classified into the following categories: data transfer, arithmetic operations, logical operations, branching operations, and machine control operations. An instruction is a command to the microprocessor to perform a given task on a specified data. Each instruction has two parts. One is the task to be performed, called the operation code, and the second is the data to be operated on, called the operand. The instruction can fit into the following types based on its size: 1 byte, 2 byte, or 3 byte instructions. 1 byte instruction includes the operation and the operand in the same byte. For instance, this one. Here the size of the binary code is just 1 byte. In a 2 byte instruction, the first byte specifies the operation and the second the operand. It requires 2 memory locations to store the binary codes. And in 3 byte instructions, it takes 2 bytes to specify the 16-bit address of the operand. Another thing to keep in mind is that here the second byte is the lower order and the third one is the high order. The notation and the convention used in specifying the operands have very little to do with the microprocessor itself, and the mnemonics are chosen somewhat arbitrarily by the manufacturer. Moving on, we will try to examine how an instruction is designed into the microprocessor, generally referred to as the opcode format. To understand the operation codes, we need to examine how an instruction is designed into the microprocessor. In the design of the 8085 microprocessor chip, all operations, registers, and the status flags are identified with a specific code. For example, all internal registers are identified as follows. Some of the operation codes are identified as follows. The instruction is completed by adding the code of the register. For example, here the add operation is represented by 1000 and the register B as 000. The accumulator A is taken as implicit. This makes the complete binary instruction as 1000 and 000. In the assembly language, this is expressed as 80H. Here is another example. To move the content of register A to register C. As we can see, the move instruction is given by the code 01, register C by 001, and the accumulator A by 111, thus making the entire binary instruction as this. In the assembly language, this is expressed as 4F. Now that we are familiar with how the instructions are formed, we can move on to examine how a program is executed. For that, we will consider a simple program like this, which performs roughly the following task, which is to add two numbers and display it on an output port 1. Once again, I would like to remind that our goal here is not to learn how to write a program, but instead learn how a microprocessor goes about reading that program. So we will not be getting into the details of how that algorithm was written. As we have discussed, the microprocessor only understands the binary code, and all the mnemonics and hex code are written just for the convenience of the human being. Now the question is, how does the microprocessor goes about converting the hex code into binary code? The answer lies with the monitor program stored in the read-only memory of the microprocessor. It converts the hex code into the binary code, and the entire setup looks something like this, where once we are done typing the hex code into the microprocessor, the monitor program converts it into the binary code. After it, the example program gets stored into the memory as follows. The critical concept that needs to be understood is that the microprocessor can only read and understand the binary code. Everything else is just for the convenience of the human beings. Moving on to executing the program. To execute the program, we need to tell the microprocessor where the program begins by entering the memory address, say 2000. Now we push the execute key to begin execution. As soon as the execute function key is pushed, the microprocessor loads 2000 in the program counter, and the program control is transferred from the monitor program to our program. The microprocessor begins to read one machine code at a time, and when it fetches the complete instruction, it executes that instruction. For example, it will fetch the machine code stored in the memory location 2000 and 2001 and execute the instruction MVIA32. Thus, it will load 32 in the register A. The add instruction will add the two numbers, and the out instruction will display the answer 7A. It continues to execute instruction until it fetches the HLT instruction, which basically tells it to stop. Now that we are pretty much done with the topic, there is this very interesting concept that I would like to discuss. The question is, how does a microprocessor differentiate between the data and the instruction code? We know that the microprocessor is a sequential machine. As soon as the microprocessor based system is turned on, it begins the execution of the code in the memory. The execution continues in a sequence, one code after another, or one memory location after another, at the speed of its clock until the system is turned off. If an unconditional loop is set up in a program, the execution will continue until the system is either reset or turned off. Now the puzzling question, how does the microprocessor differentiate between a code and data when both are just binary numbers? The answer lies in the fact that the microprocessor interprets the first byte it fetches as an opcode. When the 8085 is reset, its program counter is cleared to 0, and it fetches the first code from the location 0. In the example of the previous section, we tell the processor that our program begins at location 2000. The first code it fetches is 3E. When it decodes that code, it knows that it is a 2-byte instruction. Therefore, it assumes that the second code, 32, is a data byte. If we forget to enter 32 and enter the next code, 06, instead, the 8085 will load 06 in the accumulator, interpret the next code, 48, as an opcode, and continue the execution in sequence. As a consequence, we may encounter a totally unexpected result. And with this final concept, we have come to an end of the presentation. Thank you, and I hope you have learned a lot.